Have you ever taken a geography course? Geography would be considered one of the softer sciences as opposed to physics or chemistry. If you've ever taken a geography course, maybe you heard about tsunamis. Do you know what a tsunami is? A tsunami would be a large wave that is generated as a result of a large displacement of water. So if there's an earthquake off the coast or a landslide, an underwater landslide, it can lead to a tsunami. So the local geography of the coastline would dictate how far inland the tsunami wave would travel and how deep the inundation would be along the coast. So as a tsunami comes inland, it might hit certain structures. So when it hits a structure, there's a hydrodynamic load, which depends upon the incoming velocity, but there's also a vertical load. There's a buoyancy force. So in this example, I'll consider buoyancy. So buoyancy force, F sub B, is equal to specific density of seawater. If we're assuming a tsunami, it would be seawater, most likely. Gamma sub S, that's specific density of seawater. V sub W, volume of displaced water. That's the formula you see at the top there. So for instance, consider a 3,000 pound tank, cylindrical tank. Assume it's watertight, so we don't have water seeping in. It's subjected to a depth of water equal to 2 feet. That's what you see here. You see I shaded it in blue. It's subjected to a depth of water equal to 2 feet due to a tsunami. Will the tank float away? Will it be lifted? Okay, well, let me go back to plane geometry here. I've got a circle here. X squared plus y squared is 25. So that's what it looks like if you graph it. X squared plus y squared is 25. That's a circle of radius 5 in this case. If you remember from my original drawing, the tank has a circular cross-section of radius 5. So that's where I'm getting this from. So I've got a circle right here. Now the top portion of the circle would be y is equal to the positive square root of 25 minus x squared. That's the top part of the circle. So if you want to graph that in a graphing calculator, you'd have to put it in twice. Put it in as a square root of 25 minus x squared. That'd graph the top part, and then the bottom part would be y is negative square root of 25 minus x squared. Okay, draw a horizontal line. Y is equal to 3. That's the equation of a horizontal line. Y is equal to 3. And now do you know where that intersects the circle? So there's an intersection here. The coordinates of that point 4, 3. Then over here, the coordinates negative 4, 3. Okay, how does that look? Okay, so what I'm going to do here, drop a vertical line from this point down to the x-axis. Drop a vertical line from this point down to the x-axis. Okay, how does that look? So far, so good. What I want to find here is the area under the circle. The area under the circle. Sorry, I was fetching a colored pencil. I want to find this area right here. So this blue area, I want to find that blue area. Okay, so do you know how to do that using integration? Okay, so I set up an integral. Okay, so I'll call that A sub 1. A sub 1 is the blue area you see there. So that'll be the integral of the square root of 25 minus x squared. Integrate with respect to x. And I'm integrating between negative 4 and positive 4. Okay, how's that? Okay, so using a trigonometric substitution, for example. I remember trig substitutions from second semester basic calculus. Or you could use a table of integration formulas. However you do it, you wind up with this formula right here. what you see in the brackets is the antiderivative of the integral of the square root of 25 minus x squared. So I put the limits of integration on there, -4 to 4. So do you remember the first fundamental theorem of calculus? I'm going to implement that now. So evaluate the antiderivative at the upper limit, evaluate it at the lower limit, and find that difference to tell you what that blue area is. Okay, so I evaluate the antiderivative at the upper limit. I stuck a 4 in place of x. Evaluate it at the lower limit. Stick a -4 in place of x. So now I will evaluate the first set of brackets and the second set of brackets. Okay, so the first set of brackets becomes 6 plus 12.5 inverse sine of 0.8. Be careful, this is in radians. The second set of brackets, I've got 6 minus 12.5 inverse sine of -0.8. So now take it one step further. Okay, so the inverse sine of -0.8 is the same thing as the negative inverse sine of positive 0.8. So what happens here is this subtraction becomes an addition. Okay, so this line, I can simplify to this line, and when I calculate that, I'm getting an area of about 35.18 square units. So what does that represent again? The blue area. The blue area, approximately 35.18 square units. You could also do all this in a graphing calculator. Okay, the next thing I want to calculate is this rectangular area. The rectangular area, which would be the area that is underneath y is equal to 3, but between x is equal to -4 and x is equal to +4. So that's just a rectangle. You don't need integration to find that. It's just length times width. Okay, so when I calculate that area, it's 24 square units. 24 square units, that's the area of this rectangle right here. Okay, so to summarize, the area of this entire wedge, the area underneath the square root of 25 minus x squared between -4 and +4, I calculated that to be about 35.18. Remember that? And then I've got the area of this rectangle. What I really want is this area that I'm shading in dark blue. So that area that I just shaded in dark blue would be 35.18 minus 24. So when I find the difference of 35.18238.045 and 24, that will tell me what this dark blue area is. So I find that difference, 35.182 minus 24. So I find that to be 11.1824 square units. Okay, why did I want that area? What area is that? That's the dark blue area. That's this area. Well, why do I want that area? I turn this upside down. Okay, if I turn this upside down, remember I calculated this area right here. Go back to my original drawing. Here's a tank that I'm interested in. You see it's submerged in 2 feet of tsunami water. Okay, now do I know what this area is? Okay, I know what that area is. I just calculated it. So to calculate the amount of water displaced, that is the volume of the water displaced, I'd have to multiply this area, which I just calculated, by the length of the tank, which is 12 feet. So in doing so, I'm calculating the amount of displaced water. I need that to calculate the buoyancy. So I calculate the amount of water, the volume of water that's displaced, the 11.1824 square feet that I just calculated. That's this cross-sectional area times 12 feet. So I'm getting 134.1888 cubic feet. So that's the volume of the water that's displaced by this tsunami water. Okay, so I also want to calculate the specific density of seawater. So gamma sub S, specific density of seawater. Seawater is taken to be 64 pounds per cubic foot. So 64 pounds per cubic foot. That's the specific density of seawater. If you're using metric, it's 1,030 kilograms per cubic meter. I should take a magnification factor for this. So multiply this by 1.1. Okay, now what is that 1.1? It's a magnification to account for the a magnification to account for the flotsam that is in the seawater. The flotsam, the stuff that's floating around in the seawater. So I've got a gamma sub s. Okay, that is the specific density of seawater, 70.4 pounds per cubic foot as my specific density of seawater. Okay, so now the buoyant force. Okay, remember F sub B, gamma sub S, which I just calculated, times V sub W, which I also calculated. You see me putting the appropriate numbers into the formula. So now I take this over to the other side. Ran out of space on this slide. Oh, okay, so if I multiply those, I'm getting about 9,447 pounds. Okay, how do I know it's pounds? The factor label method. Cubic feet will cancel with cubic feet. So that leaves me with 9,447 pounds. Okay, so will this tank be carried away by the tsunami wave? The original weight of the tank was 3,000, remember that? 3,000. Okay, so I noticed that this is quite a bit bigger than 3,000. And I'll just say 3 kips. 3,000 pounds. So a 9.447 kips is greater than 3 kips. So it could be carried away unless it's tied down. So such a tank should be tied to the surface. If it's designed to be on a concrete pad, it should be fastened to that pad, otherwise the tsunami wave will carry it away. Of course, that doesn't take into consideration the hydrodynamic force. As I said earlier, a tsunami wave is going to generate some hydrodynamic force, so that would also be an issue.